Today we are going to take a look at reactions in aqueous solution. So remember, aqueous just means a solution in water. Water is always the solvent in these types of solutions, but water is not the solvent in every type of solution. So when two aqueous solutions containing ions are mixed, a double replacement reaction occurs. Okay. And so what we are going to do now is we're going to look at a double replacement reaction. And we're going to start with just the regular formula. I'm going to write it up for you guys. Then I'm going to break it into its complete ionic equation, which is just every ion in both solutions as a separate thing. I'm going to show you how to write that. And then we're going to go through and we're going to cancel out anything that's on both sides of the arrow at the same time. And what that does is it gives us our net ionic equation, basically just the things that interact. All right, so what we're going to do is, I think that was my pen. There we go. So what we're going to do is we are going to start with a equation, which is 2NaOH plus CuClAq yields 2NaCl. This should have a 2 next to it. So there is a typo in your notes as well. This should be CuCl2. CuCl2AQ. So if you would just throw that 2 in there in your notes, otherwise this isn't going to make any sense. 2NaClAQ and then plus CuOH2, and that is a solid. So right now you can just look at this equation and you can tell that a precipitate has formed. Copper hydroxide is not soluble in water, so it precipitates out and becomes a solid, which is really cool. All right, so when that happens, whatever the solid is, stays together when you start splitting it into the net ionic equation, because that solid is not dissolved in the solution, so it's not separated out into its individual ions. It stays as a compound. Okay, so this is your original. And now we're going to do the net ionic equation. So the net ionic equation, like I said, is just splitting these. So you're going to look at each compound, figure out where the cation and anion is, and you're just going to do this so that you kind of know what you're doing here. And then you're going to rewrite it. So because there's a coefficient of 2 in front of NaOH, each of these is going to have a coefficient of 2 as well when you write them in the net ionic. So it's going to be 2Na plus, because sodium has a positive 1 charge, and then AQ plus 2OH, 1 negatives, AQ, because hydroxide is a polyatomic with a 1 negative charge, plus, and here we have 1 copper, Cu, and because we know the charge for chlorine is a -1, we can guess that the charge for copper is a +2. So it's going to be 2 plus AQ, okay, plus 2 Cl minus AQ. Okay, so now the question is, why did I put a 2 in front of my chlorine? I'm taking the subscript because now that it's not in compound, it's just the ions I'm talking about. You can use the subscript as a coefficient. Okay, so that subscript becomes the coefficient for the ion. Okay, and now we're going to look over here on the right-hand side, and we again have 2Na, 2 sodium. And this is going to be 1 plus, sorry, not 2 plus. So just a little plus there. Again, AQ plus, and again, you've got that coefficient applies to the whole compound, so you still got 2 chlorine ions. Okay. And then you're going to leave the last thing alone because it's a solid and it's not dissolved. So it's going to just be CuOH to solid. Okay, so this is called the complete ionic equation. Sorry. We are making the net ionic equation, but you have to start with the complete ionic equation. Okay, and then in your notes, you already have this done, but I'm going to walk you through how it works. Now you're going to use the arrow here as a guide for what you're going to cross out. Okay, and you only cross out ions that are on both sides of the equation. Okay, so that means that if it's in this compound, you're going to leave it alone on the other side. Okay, so we're going to check sodium is on the left as an ion and on the right, and there's 2 on both sides, so I can cross the whole thing out. Da-da. Okay, hydroxide's an ion on the left, but it's in a solid compound on the right, so I'm going to leave that one alone. Copper is the same way. Copper is over here as an ion, but on the right-hand side, it is a cation in a compound, and it is solid. It's not dissolved, so I'm going to leave that alone. And then the next one I'm going to cross out is this 2Cl because it's on both sides. Okay, so what I've done is I've taken all of the spectator ions, all of the ions that don't go into a product that I can measure and collect, and I've moved them off to one side. And now I'm looking at only the things that create a product. Okay, this is really useful for when you're trying to get a specific product. If you do this equation and you figure out what is going to become a solid, then you can look at what you really need to focus on adding, because the more concentrated those ions are in your reactants, the more likely you're going to have that product. And so our net ionic equation, okay, is taking just the things that aren't crossed out. These are the things that actually react. And then saying what compound do they form. Okay, so the net ionic equation takes anything that doesn't form a solid product or a gas or something that's not an aqueous solution out of the picture, because you don't care about those. They're not creating what you're looking for. Okay, and you're only looking at the things that react to create a measurable product. Okay, because remember, when things are in aqueous solution, it's very hard to measure them. They're still floating around in the water. So unless you're measuring things like pH or you're plugging it into a spectrometer, um, you really can't tell what those are anymore. They're just dissolved and they're in solution. Now you can figure it out mathematically and chemically, but you can't measure it. When you get a product like copper hydroxide, copper 2 hydroxide, sorry, um, that's a solid, you can then pour off the solution and dry it and weigh it and measure what you've gotten. And so that's really what a net ionic equation is for. It's for predicting your measurable products from a reaction in an aqueous solution. And most often you'll use this with things that create precipitates or solids, because again, gases are hard to collect. So we tend to stay away from them, especially when we're doing like the real basic, like high school level chemistry. When we're trying to do things where you're trying to quantify or measure how much product you're getting. And that's really it for ionic equations. There's a exercise I want you guys to complete. Please complete it with a partner. Okay. Use that rally coach method that we've been practicing, where you're walking the other person through how to do it, because it not only does it cut your workload in half, it also gives you some practice at telling people how to do it. And the more you tell somebody how to do something, the more you remember it. Okay. But